I love these conferences where we actually are ahead of time. It never happens with the lawyers, never. Usually we're always over time. Okay, so I have been told that because we are ahead of time, I can actually start the Singapore panel. And so the Singapore panel really is made up of 3 speakers, and I would like to invite them to come and join me on stage for their presentations. We have Professor Matthias Roth, who is from the National University of Singapore. He is an associate professor in the Department of Geography, and his research examines how land use changes affect local climates with a particular focus on cities. And we have Dr. Eric Velasco from the Molina Center for Energy and the Environment. Dr. Velasco investigates the impact of urbanization and climate change on the atmospheric environment and biogeochemical cycles. The primary aim of his research is to provide reliable scientific information for making effective solutions to improve the atmospheric environment while enhancing sustainability. And the third speaker on the panel is Professor Benjamin Kashaw from the Lee Kuan Yew School of Public Policy here at the National University of Singapore. Ben is the Lee Ka-shing Professor in Public Management and Director of the Institute for Environment and Sustainability here at the university. Dr. Kashaw specializes in global and multi-level environment governance, comparative public policy, and transnational business regulation. And with that, I would like to invite the 3 speakers to join me here on stage. Each speaker will speak for about 15 minutes. I will open the floor to questions and answers for about another 15 minutes. Is it one by one? You want to go? Okay. Oh, okay.
Yeah, so there's no screen here. Okay, it's coming up. Yeah. Here it is. Very good. And this work? Forward, backwards, up and down. Okay. I hope. Oops. But it's very unusual to be the first speaker in a conference or summit like this. Usually they put me in the last day when everybody has left, I guess. So this is a little bit different here. So, but yeah, I'd like to thank the organizers first for inviting me, in particular, Luisa Molina to suggesting my name and Tomire Oda to sending out the invitation afterwards. Thank you very much. I'm very honored to be able to speak here at this summit. So I was asked to talk about how land use and land cover changes affect the local climate with a emphasis on cities. This is my particular expertise. And I thought I would add another section at the very end on monitoring air temperature, which is a little bit more relevant than also to the main theme of this summit, I think. So I have 3 sections. It's a little bit of a 101 of urban climatology, and then I'll end up with some ideas and thoughts on monitoring climate variables, and as I said, in particular, air temperature in cities. So yeah, if you look at these different scenes here, even if the background climate is the same across these 4 geographic locations, each of these locations you can see here has a very particular local microclimate. And this is an outcome of differences in energy partitioning at the surface. And so this is the surface energy balance. So it's going to be a little bit technical at the beginning here with what I want to show you. So if we have transformation of landscapes, and these are 2 scenes from Singapore here, you could imagine, or you can very well envisage that the microclimate on the left-hand side is very different from that on the right-hand side. So if we change a natural surface like the one on the right-hand side into something that's made up primarily of stone and concrete surfaces, of course, the energy partitioning at the surface will be completely disrupted. So look at this as kind of, okay, we have incoming energy. What's happening with this energy? Where is the energy going to? So the energy source primarily is the sun. How is this energy being transferred into other proportions or portions of the so-called surface energy balance? And this disruption happens here on the right-hand side, because all of a sudden we have a replacement of natural vegetated surfaces with concrete surfaces. So there is less water available at the surface, less evaporation. We have a 3D morphology as well, which is primarily built or made up of concrete. So the solar radiation, how it interacts with this very complex 3D surface, is completely different than on the left-hand side. And we have also addition of anthropogenic heat through the activities of the human beings. So why is this important? Why is this partitioning at the surface important? It's important because that partitioning determines the so-called state variables, such as temperature and humidity and others as well. So if we're looking at temperature, the temperature is an outcome of the energy balance partitioning at the surface. So just to add this schematically as well, the energy balance over a vegetated surface like on the left-hand side is relatively easy, can be easily described by, you have incoming solar radiation, outgoing solar radiation, long-wave radiation. So we have a Q star, the net radiation, which is the input into the system. Where does the energy go to? It goes into sensible heat, heating of the atmosphere. It goes into evaporation, depending on how much water we have at the surface, and some of it goes into the ground as well. On the right-hand side, this schematic or this partitioning is much, much more complex. And one of the outcomes of this is the so-called urban heat island. The urban heat island effect is probably the most recognized and the longest recognized of any anthropogenic effect. It's not anthropogenic global warming, because the urban heat island has been around for a long time and has been investigated for a long time. It goes back more than 200 years. So I'll say a few words just about the urban heat island because of its importance in as one of the possible outcomes of disruption of the energy balance at the surface. So when we talk about the heat island in a city context, we distinguish between different types of heat islands. We have the so-called surface temperature heat island or surface heat island. So this is just the extra warmth in the city measured as the surface temperature compared to the surface temperature of a lesser developed natural vegetated surroundings near the city surface or near the city itself. Then we have the so-called canopy layer heat island. So this is the heat measured at screen height, about 2 meters above surface. This is the one that is probably most important to our, in terms of practical implications, because it determines thermal comfort, for example. It's the area, it's the portion of the atmosphere where people live in. It's within this canopy layer, which is kind of somewhere between the surface and the top of the buildings. But the extra warmth of the city actually extends up into the higher atmosphere and can be advected downstreams for, in the case of large cities, hundreds of kilometers. This effect is also strongest at night time. So I'm just going to show 4 results of how the city can affect the local climate. So the first one is now on, again, on the canopy layer urban heat island. This is from a recent publication here. Where we measured the heat island at more than 20 places, or we measured near surface air temperature at more than 20 places across different landscapes or neighborhoods within Singapore. And then we are taking differences. So we have a reference site, which is a undeveloped or as undeveloped as it's possible in a city context, such as Singapore, which is outside of Singapore. And then we subtract that temperature there from the temperature measured at different neighborhoods within the city. And so our reference site here is this area in the northwest of Singapore, Lim Chu Kang. It's kind of a lightly forested area, so it's primarily vegetated, but it has some individual trees. So this is our reference, and then we compare the temperature in different areas in the city with this temperature here. And we plot the, in this case, the diurnal variability of the so-called heat intensity, so that difference. So the x-axis goes from noon to midnight in the center, and then noon again on the right-hand side, and the y-axis is the so-called heat and intensity, that difference. And if we compare the natural vegetated area with measurements in the city center, like is indicated on the top right-hand side. So this is a location close to Orchard Road. This is in the center, in the commercial Singapore, and we subtract the temperature from Lim Chu Kang, we see that we have a maximum of this temperature difference somewhere in throughout the night. And on the long term, this temperature difference can be up to 4 degrees C. So this is an additional warming in the context of a downtown city, which is 4 degrees warmer than the rural surroundings. Of course, during daytime, the difference is less, but it's still a positive difference. If you go to a lesser developed site, like on the top left-hand side, more residential side, the warming at night is still about 3.5 degrees C. And if you go to an industrial site, it's about still close to 3.5 degrees C. And it's only if you go to a lesser developed, kind of a single family residential site, where the temperature is, or the temperature excess during nighttime is only about maybe 2.5 degrees C. But these are long-term averages. I should point out this is under ideal conditions when we have no clouds, we have no winds or weak winds, and dry surfaces. So this is, if you look at this on the long term over average across all the different weather conditions, we actually see that the mainland Singapore is warmed or experiences a additional warming due to the presence of the buildings, the city itself, from about 1 to 1.5 degrees C. So it is the long-term average throughout the year, all the seasons, day, nighttime, and all the weather conditions. We also know from measurements from the Singapore Center for, or the Climate Center for, or the Center for Climate Research Singapore, that the warming in Singapore since the 1970s has been about twice that of the global average, the background warming. So the anthropogenic global warming everybody's talking about, which is roughly 1 degree C over the last, I don't know, 100 years or so. It's about 2 degrees C in Singapore. So this extra warming due to the presence of the city explains about half of that global warming measured in Singapore. So this is one example of a local climate change effect. I should point out this is also research done in collaboration with Eric Velasco, who is the next speaker just after me. So another effect here is the anthropogenic heat flux, which is a flux which only arises in cities and not outside. On the left-hand side, we see the urban fraction of Singapore. Let's just concentrate on mainland Singapore. Let's just ignore Malaysia in the north, the red parts. And on the right-hand side is an estimation of the anthropogenic heat flux. So this is an additional component of the energy balance, which not arises anywhere else, just in the city. And in certain areas, it can be quite significant. On average, it's not a major input into the energy balance, so it doesn't really explain the urban heat dome effect. But locally in the industrial areas, as you can see maybe in the southwest of Singapore on Jurong Island, we have a lot of petrochemical industries, and locally we can have very, very high point sources of anthropogenic heat fluxes up into the thousands of watts per square meters. But these are just emissions at the top of chimney stacks, basically. If you average them out across a larger area, it's much less. But locally, we can have significant anthropogenic heat flux contributions to the energy balance. So all of this, the disruption of the surface, the addition of buildings, more roughness in the city, anthropogenic heat additions will also disrupt other parts of the climate, not just the temperature. And we have done some investigations on the effect of the presence of the city on rainfall, for example. And we've seen through modeling approaches that the rainfall intensity of especially the convective rainfalls, so these are the mid-afternoon rainfalls, which you regularly get during certain times of the year here at around 4 or 5 p.m., that the intensity of these rainfalls is actually increased through the addition of the city. On the left-hand side, you see 2 model simulations, one, the green one, when we have no urban area in the model itself. The red one, we add the city surface of Singapore, and you can see the peak intensities increase quite dramatically at around 3 or 4 p.m. And this is, we think, or at least the model suggests, this is due to the presence of the city. On the right-hand side, again, on the left-hand side is the spatial distribution of rainfall intensity without a city surface. So we just have vegetated surface, the natural vegetated surface which we would have here if the city wasn't here. On the right-hand side, we add the city surface. And you can see that over Singapore, but also north to it, where Johor Bahru is, just kind of the next city up in Malaysia, that over those areas, the rainfall intensity is increased. Other examples, or the last, well, 2 more examples of the influence of the city surface on the local climate. Here now I'm going back to the energy balance. As I said, it's very important to understand the energy balance and the partitioning at the surface. So on the top right-hand side, the energy balance is written out for a city surface. So we've measured this in Singapore here, and again, this is in collaboration with Eric here, maybe you're going to show some results from here as well. I'm not going to say much because I expected you to actually do this as well. So we had an energy balance and CO2 flux site here in Singapore, which we were running for about 10 years. And you can see the setup on the right-hand side. And with this setup, we can measure all the energy balance fluxes and the CO2 fluxes at the top of a volume, the volume which is indicated on the top left-hand side here. And if we measure the energy balance, it looks something like this. This is again the diurnal variability. Now we have midnight on the left-hand side. Daytime is in the center, nighttime is on the right-hand side, and the energy flux is on the y-axis in watts per square meters. So the dark black line is the energy input into the system. So we're interested in where does this energy go to? And if you look at the red line and the green line, the red line is the sensible heat flux and the green line is the latent heat flux. And what you can see is that the red line, the sensible heat flux, is much higher than the green flux, the latent heat flux. That's because it's a dry area, relatively dry area, not a lot of moisture. It's a city area. So the energy goes primarily into heating the atmosphere, not so much into evaporation. Also, what is different from other surfaces, especially natural surfaces, is the blue line, which is the ground heat flux. So how much energy of this input is going into heating the ground? And as you can see, the blue line is of similar magnitude as the red line, sensible flux. And this is what then creates the heat island at night. So this is the heat that's being stored during daytime in the buildings and is then being released at night. And it creates the heat excess in the city at night. And the last example is the CO2 flux, which we measured at the same time. Just don't worry about the details. Just look at the black line with the black dots. That's the long-term average. And the main thing to realize here, it's primarily positive throughout the entire day and also throughout all the seasons. So the city surface, as we know, is a net source of CO2 at all times, which is very unlike surfaces which vegetated surfaces which would show negative heat fluxes during daytime, as shown on the left-hand side here. This is from a tropical rainforest in the Amazonan Basin. So nighttime fluxes here are positive as well, respiration, but during daytime, a vegetated surface like this will take up much of the CO2, and probably the net effect is a net uptake of CO2 by vegetation, as we know, throughout the day and year, etc. But city surfaces, as we demonstrate with these observations, are positive throughout all times of the day and seasons. So just a couple of slides on monitoring temperatures. And this is based on an initiative I've been recently involved in with WMO, where we produced a guidance on modeling and monitoring the canopy layer heat island. So this is a guidance document that will be sent to all the meteorological services across the globe. And if they're interested in monitoring the temperature in the city, they should follow these guidelines, because as you can imagine, measuring the temperature in a city context is a little bit more complicated and complex than in an open grass flat surface. And most of the WMO guidelines pertain to that more ideal case, not the city case. So what we suggest here for monitoring of air temperatures, and this would apply to other variables actually as well, is monitoring is important for the provision of urban services, to evaluate the ongoing assessment and the impact of urban development over time. So we need monitoring, we need over decades, not just years, to be able to monitor the impact of urban development on the air temperature, for example, and how this relates to the climate change context as well. So the goal is really to provide long-term information, which is not really readily available in cities yet. And for this, it's really important to partner with other agencies, primarily probably the National Meteorological and Hydrological Services, government agencies, research institutions, because through this, it's possible to have a more comprehensive and comprehensive approach, which includes both modeling and observational monitoring, which then can be made available to the entire community. And also, I think this collaborative effort is needed to streamline the operational aspects, such as siting of the sensors, where to put them, to be able to leave them in the same place for a long time, for the monitoring, for the maintenance of the monitoring systems, which is a long-term commitment, etc. In terms of monitoring canopy layer urban heat islands, there are basically 4 approaches which we suggest. We can just have the traditional urban-rural pair approach. So one site in a city center, one outside in the lesser developed rural area, and then take the difference. Or if we have more resources and we're more ambitious, we can have sites, city sites in individual neighborhoods. Let's say a downtown neighborhood, a commercial neighborhood, an industrial neighborhood, a residential neighborhood. Or we can have a regular set of sensors spaced out across maybe a modeling grid if we want to evaluate models. Or we can just take advantage of citizen weather stations with an irregular but very dense network. But this approach is much affected by data quality issues, but it has its role in some contexts. And this is just one example of good practice, a city, an urban-rural pair of stations from Łódź in Poland. On the left-hand side is the urban station, on the right-hand side is the rural station. There's some bad examples of as well, where the city station is in an urban park, for instance, and then this is being kind of looked at as the representative station of a city. So just to finish off with final remarks, yes, cities are dramatic examples of local climate change. I really want to make this point here. Cities have a local climate change, which is in addition to the global background climate change. And this affects all aspects of climates. And if we want to monitor within a city, we have to take note of this large variability at small scales, neighborhood scale, local scale. On a micro scale. Monitoring into the future includes future changes of the areas as well, because the city surface is dynamic. but also the background climate change. Because the dynamic nature of the city surface, it's really important to collect site metadata, so we can actually analyze the observations and relate them to possible changes in the immediate surroundings of the sensor site. So this is needed for systematic, or if there is a need for these systematic and multifunctional infrastructures which couple observations with Earth system models to serve operational and research purposes. And of course, this initiative, which the GEMM initiative discussed at this summit, is obviously sort of directed at this. And I think personally that integration and homogenization of the monitoring, which is measurement and modeling, not just measurement actually, of that data, there needs to be integration between the national hydrological and meteorological sites, services, but also other WMO initiatives such as the GCOS initiatives, because it's a long-term investment, it's a long-term thing. This cannot just be done by individual researchers, which may then disappear from the scene after a while, and then the stations are left unattended, and there's no more data quality control, no metadata collection, etc. So this needs to be a bigger initiative. Yeah, so many people have contributed to the results I've shown here, and I'd like to thank you very much for your attention. Thank you.
Good morning, everybody. Welcome to Singapore. First, I would like to thank to putting all this together to Tom Oda, Tom Bayer, Jolene, Lin, and Luisa Molina for the invitation to contribute to this effort. Well, now it's time to talk about Singapore's air quality management and climate change monitoring. First, we have to say that since its inception as an independent nation, Singapore understood very well the importance of solving all environmental problems for the well-being of its own population, as well as a strategy policy to convincing foreign investors that it was a well-planned and sustainable city. Singapore follows a unique strategic based on the first air quality assessment was conducted over 50 years ago in 1970. The results, the findings of this initial assessment were used to enact the Clean Air Act 1 year later. In 1999, it was replaced by the Environmental Protection and Management Act, and this one has been updated regularly. Now, Singapore follows a unique strategic based on an integrated urban and industrial planning, strict enforcement programs, pragmatic and cost-effective policies, and a flexible approach to changes in technology. All of them together have allowed Singapore to achieve a dynamic economy, as well as a high-quality living environment. The Ministry of Sustainability and the Environment formulates and reviews all strategic policies related to Singapore's environment. The National Environment Agency is the statutory board that implements such policies. Air quality monitoring, air quality management, and climate change mitigation are part of NEA agenda. The Ministry of Sustainability and the Environment, MSE, is committed to achieve a clean and sustainable environment, as well as building a resource-efficient nation and a climate-resilient society. MSE, together with other 4 ministries, launched in 2020 the Singapore Green Plan. This plan charts ambitions and concrete targets over the next 10 years, aiming to reach sustainability by building a circular economy and by becoming a net zero emission nation by 2050. Now, let's go to enter in matter. About air quality, Singapore comes with an air quality monitoring network of 18 stations measuring air pollution at ambient level, I mean above the urban canopy, and 4 at roadside. sulfur dioxide, PM10, nitrogen dioxide, ozone, carbon monoxide, and fine aerosols, I mean PM2.5, are the 6 criteria pollutants considered in Singapore. For air quality purposes, the city island is divided in 5 regions. Every hour, NEA publishes the rolling average concentrations of these criteria pollutants, and with them, calculates a pollutant standard index. In addition, every hour provides an air quality descriptor based only on PM2.5 ambient concentrations. This is for sake of informing about the instantaneous air quality conditions. Now, the question of $1 million. How many Singaporeans are in the audience? Please raise your hand. Okay, how many people live in Singapore? Well, not so many. Well, let me ask you, what do you think about this? Do you think air pollution is still a problem here? Yes. Yes, right, exactly. We cannot rate air quality problem in Singapore as those in other large cities across the region, such as Manila, Jakarta, Bangkok, etc. But air pollution is still here, it's still present. And yeah, the worst episodes are triggered by massive wildfire across neighboring Indonesian islands. But also we produce our own pollution. We have our own emission sources, industries, refineries. We have the busiest port in the world, just a few kilometers from here. And Singapore doesn't count with an emission control area. That means that the ships can burn whatever fuel they want. Changi Airport is also a major source of atmospheric pollutants. We have over 1 million vehicles on the roads, and we cannot close eyes to our own very particular emission sources, such as the burning of fake money during the Hungry Ghost Festival. And besides, just crossing the channel to the north, we have Johor Bahru, and to the south, we have Batam in Indonesia, and together make up a metropolitan area of 8.4 million inhabitants. And in this time series of fine aerosols, we can see that air pollution exceeds almost every day international thresholds in Singapore. Here we are using as reference the interim target number 4 proposed by the World Health Organization of 25 micrograms per cubic meter a year ago. But I have to say that in Singapore, we never exceed air quality standards. And it is because we don't have standards, we have targets. And there is a big difference between having air quality standards and targets. But well, let's go to assume that targets are correct. How does Singapore targets compare to international thresholds? Well, they look a bit lax. Carbon monoxide is the only pollutant that is not a problem here. But sulfur dioxide, nitrogen dioxide, ozone, PM10, yes, present relatively high concentrations, not extremely high, but they exceed those international thresholds. And as any other modern city nowadays, Singapore struggles controlling pollution by fine aerosols. This is not only Singapore. Many other large cities around the world are struggling to control, to reduce ambient concentrations on fine particles. And this chart is used to inform in general about Singapore's air quality conditions. At first glance, you will think that air pollution is not a problem at all. But if you pay close attention, you will see that authorities are not lying, but are not telling us the whole history. And air pollution causes every year almost 1,400 premature deaths. It represents 24 deaths for every 100,000 inhabitants. And it has a cost that reaches 2.4% of the national GDP. That is a lot of money, no question at all. And when we come across advertising like this, we may think that something weird is in the air. And it is. Asthma can be triggered by many reasons, but air pollution is one of the most important reasons. And sadly, Singapore presents one of the highest asthma rates worldwide. 1 in every 4 teenagers suffer of asthma here. And to wrap up the discussion about air quality monitoring, we can affirm that Singapore has a robust air quality monitoring network, but we do not know where the air quality monitoring stations are located and which pollutants are monitored at this station. In addition, real-time, ambient concentrations of every criteria pollutant are not available. We only get access to real hourly concentrations, no rolling average concentrations of PM2.5 and NO2. And records from past years are not open to the public. And similarly, we don't know anything about precursors. For example, we don't know anything about the volatile organic compounds in Singapore, and they are very important because they boost the production of secondary pollutants such as ozone and an important fraction of PM2.5. In the same line, we don't know anything about the chemical processes occurring in the hot and humid atmosphere of Singapore. And meanwhile, we don't know these processes, these mechanisms, we won't be able to understand the production of these secondary pollutants, such as fine aerosols and ozone. And in turn, we won't be able to explain changes over time, and we won't be able to propose better air quality policies. And the same is true for aerosols. We don't know which is the chemical composition of the particles that we breathe in Singapore. And about emissions inventories, well, in Singapore, we only count with emission estimates for sulfur dioxide and greenhouse gases. According to my knowledge, in Singapore, we don't count with a spatially and temporally distributed emission inventory that can be used for air quality modeling purposes. However, luckily, we can make use of these international initiatives such as EDGAR, and retrieve, extract for EDGAR databases, Singapore emissions, and learn how these have evolved throughout the time. About air quality modeling, again, according to my knowledge, I don't know of any operational air quality model in place in Singapore. Air quality models are needed to understand, to investigate past episodes, as well as to evaluate the effectiveness of new environmental policies. Nowadays, many environmental agencies are running air quality models on a daily basis as a forecasting tool to be able to advise people, to warn people about potential air quality episodes. And let's jump to greenhouse gas emissions inventories, to greenhouse gas mitigation. As part of its national communications to IPCC, Singapore updates every 2 years its emissions inventory. This emissions inventory is built using bottom-up approaches. Activity data and emission factors. It's a straightforward methodology, but it's subject to uncertainties due to the data or the quality of the activity data and representativeness of emission factors. Again, according to my knowledge, I don't know of any validation system in place based on observations. As Matthias introduced, as part of our own research, we deployed a eddy covariant flux tower in a low-rise neighborhood of Singapore for a number of years. And with this tower, we were able to measure directly and continuously carbon contributions from all major and minor emission sources and carbon sinks from a footprint of a similar size of a complete neighborhood. And this is what we got. Fluxes, carbon dioxide fluxes higher at night, lower during daytime. And it looks a bit suspicious. We may expect higher emissions during daytime. To explain this pattern, we built our own emissions inventory for this part of the city, and we found a disagreement. The disagreement was due to vegetation. During daytime, we have the photosynthesis effect, and at night, we have respiration. To verify, to validate our findings, we conducted a series of experiments to evaluate the contribution of each individual component of the green landscape. Putting together all these components, soil respiration, carbon uptake by photosynthesis from turf plants and trees. Also, we included contributions from maintenance activities such as mowing, trimming, pruning, etc. We found that the urban vegetation in Singapore, at least for this part of the city, is capable to offset up to 8% the anthropogenic emissions. But this is only true under an ideal waste disposal management. If we send all our garden waste to an incinerator, we lost all carbon gain. Extending our findings to the entire city, considering the 112 square kilometers covered by turf and 6 million trees, we found that Singapore green landscape is capable to offset almost 1% the anthropogenic emissions of greenhouse gases reported in the official emissions inventory. And to close my talk, if you are interested in learning more about Singapore's air quality management and climate change mitigation policies, I invite you to read the papers that we have written about these two topics. My take-home message, 2 words: transparency and accountability. Whatever achievement Singapore can make in solving environmental problems is of extreme relevance across the Southeast Asia region. And this is because many cities see Singapore as a model city, as the city to follow. Thank you.
Thank you very much. I'm Ben Cashore, and I'm both the Lee Ka-shing Professor in Public Management of the Lee Kuan Yew School of Public Policy. And also as of 4 months ago, as Jolene mentioned, I direct the Lee Kuan Yew School of Public Policy's Institute for Environment and Sustainability, IES. And so I was thinking today about what to present, whether I focus on the EYES mission or my own work. And I'm going to sort of combine both a little bit to highlight some overall big picture questions that I think are relevant for this workshop and for as we go forward in general about how we integrate work on monitoring and research into the policy process. So I want to start by saying that EYES was created because there was a recognition that both in Singapore and globally, there has been really outstanding work being done on the scientific side, on the biodiversity side, on the engineering side, on the technology side, and even on the law side when it comes to thinking about the climate crisis and related sustainability challenges. But that research hasn't been well connected to the work on policy, politics, and governance. It's almost like there's 2 separate communities, the STEM technical side and then the politics side over here. And they have different frameworks, different methodologies, and different ways of seeing the world. But we hypothesize that if we're going to try and improve and close the gap between very clearly stated government and societal policy objectives, as highlighted by the Paris Accords 1.5-degree objective, that we need to do a better job of finding out how we then can identify policy tools that are consistent with those objectives, rather than ones that are developed aspirationally in the hopes of meeting those objectives. But as you all know from the last 30 years, well-intended efforts have fallen short of meeting these goals and objectives to which we are all devoting our time. So what I want to do then is reflect a bit on my own work in this regard about trying to close the gap between policy tools and governance, the research we do on these questions, and then the outcomes that are being achieved. And the metaphor that we use at EYES and that I want to think about today is this metaphor of fit for purpose policy analysis. And my take home is that any research that you want to do and present during this workshop, but even more important, following this research, this workshop, located in a broader political and policy design world that incorporates what you're doing, but also goes beyond it. So that's my take home. And for that reason, I'm going to begin and do a lot of sort of big conceptual work, as well as looking at some data that we're doing in the lab, and then offer some research questions that I think can locate a lot of the concerns we all face. So I want to begin by recognizing that today we are definitely in what one can call a transformation agenda. Anybody working in the space of climate change, biodiversity, and livelihoods, including the data and evidence-based approaches being taken in this workshop, are all solidly behind some kind of way of achieving a transformation. We know that the world is hurtling towards a catastrophic ecological and economic and social collapse, and we know that transformations are needed to achieve those outcomes. In fact, everybody agrees now we need much more attention to the climate crisis, which of course this workshop is tending to. Likewise, the mass extinction crisis, which is related to this one, and of course, equity concerns, how we think about and draw on the most vulnerable peoples in managing these transitions, which has led to this notion of just transitions as well. And I got to say, in this regard, Singapore's efforts the last 3 years have been nothing short of dizzying. As a policy scientist, I often say to governments who are doing so much so fast, could you please slow down? So we can't actually analyze it fast enough, right? And I was just at Sharm, and others of you were too, and Singapore had its first ever pavilion at the climate COPs, and it had every day around 5 or 6 workshops of efforts designed to bring the private sector, governments, academic, societal actors together on decarbonization pathways. It's extraordinary what's happening, not just in Singapore, but also around the world. So we're at a very, I think, pivotal moment in that from Singapore to my home country of Canada, governments now accept the challenge, and the idea now is to actually how to draw on different knowledge sources and different innovations to achieve these goals. So it's quite an exciting time, as you know. At the same time, there's a more sobering story of the last 30 years of sustainability governance, going back to the Rio Earth Summit, so Agenda 21 of Sustainable Development, which basically was the first place to document what we now call the Sustainable Development Goals, the SDGs. But the SDGs are actually not really new in terms of the ideas and measures behind them. They're just reinforced in a more clear and cohesive way. And we've had all kinds of policy interventions, evidence-based, data-driven policy interventions since this time to try and achieve and address the climate crisis and related sustainability goals. And we've really reinforced this idea of evidence-based for finance and carbon for carbon markets, including forests and other areas that relate to decarbonization. So we've had this 30 years of efforts, including a lot of monitoring of the very things you're doing in this room. And yet I should just reinforce, the IPCC reports have been heralded as places for documenting this kind of evidence-based, data-driven approach, and including the previous 2 speakers. We've had significant evidence for the last 30 years, and we're continuing to gather more. And so there's no question on the research side, we've done it very well. And as a result, in fact, there's progress in some SDGs. In fact, in economic growth and poverty alleviation, we've used evidence to actually intervene and create policy tools and governance approaches that have led to great improvements in people's lives around the world, including in Southeast Asia. And yet, as you know, on SDGs 13 and 15, climate and biodiversity, the challenges, of course, are getting more acute. You all know this. This is why we're here in this room talking about these questions. But it's worth thinking about, right? Because all these meetings we've had, IPCC, the politics, science, policy tools, the innovations, have not correlated with the outcomes we've wanted, right? It's the awkward statistic here that is the most high-level evidence-based data-driven approach you can possibly take. And it's coincided with continuing tropical forest loss, of course, emissions in general, and even species extinctions have all become more acute and more worse. So my question then is, when you're having the talks today, how do you want to locate research on measurement and reporting? Where do you want to locate yourselves in this story? What does the evidence-based turn do for these questions? I often think it's quite interesting, because even in political science and governance studies, about, I don't know, 10 years ago, the metaphor evidence-based research emerged as the way to coalesce our work. And I thought, that's fascinating. Evidence-based research is a really good idea. And I thought, what did we do before this metaphor? Did we not do evidence? What did we do before it, right? I was pretty sure we did evidence-based research before evidence-based research became a term. And I realized the actual answer was that evidence-based meant something specific. It meant getting data from the past to extrapolate to the future. But what about future data that hasn't happened yet, that we therefore can't extrapolate history from? What about innovative ideas where there is no evidence yet, but we create new evidence? Does evidence-based undermine innovative ideas? And I think it might actually. And yet your workshop the next 2 days, I think, could be useful for creating innovative ideas to create new future evidence that you don't yet have. And therefore evidence-based ought to be put in its place. Moreover, evidence-based kind of move things towards a technical direction. But what about the politics? What about how we think about the world itself? Can't really be totally adjudicated by the evidence-based turn alone. So my question then is, how do we locate research and evidence in the context of helping Singapore and other countries accelerate their projects for achieving 1.5? How do we actually think about new futures and new evidence that we can help governments, therefore, help design and achieve more impactful policies that break from the past of lofty efforts and lofty goals and lots of evidence, but suboptimal outcomes? So to do that, I thought, let's first think about then what evidence does for responsibilities for these questions. And its charm, wow, countries were jockeying for, and companies were jockeying for, and NGOs were jockeying for different ideas about responsibilities based on the same evidence. Or they looked at different evidence that was all actual evidence-based data. So a lot of countries look to country level emissions, right? So we hear a lot now that China has, this is actually from 2000, but China is now the worst emitter compared to other countries. Right? It's past the United States. So that's one level. You blame countries, or you assign countries responsibilities. But of course, the problem with that is that you can draw a line around any 1.3 billion people in the world, and they're probably going to be the largest emitters. But likewise, if you decided overnight that China's 33 provinces were now countries, it wouldn't matter anymore as emitters, right? So all of a sudden, ooh, how we conceive of problems matters for how we look at the evidence, which I know you know, but it's worth repeating because there are other ways of thinking about this, and this is per capita, right? And all of a sudden, Canada, my home country, is all of a sudden as bad as the United States and even worse than China, whereas before, Canada didn't even figure, right? But now it actually really matters over here. So how we think about responsibilities, our conceptions, matters for how we think about the evidence you're looking at today. I like this one the best. Historical responsibility. I have 3 minutes remaining. Okay. On this one, if you look at all the CO2 emissions in the atmosphere, and as you know, we know from the evidence that carbon sits in the atmosphere for 300 years. So whether it was put in 50 years ago or 90 years ago, it's the same for the climate crisis today. 92% of emissions are owing to Annex I countries' outcomes, right? But a lot of the discussions we're having about what to do don't reflect that data. They reflect, actually, a lot of the Annex I countries now are actually going to impose carbon border adjustment mechanisms on developing countries for not doing enough in the climate crisis. So they were almost having reverse logics in our policy tools. So I've only got 3 minutes. Oh, of course, I like this one too. Class and wealth are rarely thought about in terms of responsibilities, but the evidence is quite clear that class and wealth also explain responsibilities as well. So to me, the first order task then is how to conceive of the climate crisis itself, and then to review and assess what perspective our data reinforces. Now, I haven't got time to go through this chart in detail, but I want to give you a brief hint of what we do in my lab. around linking data to the way we think about policy problems. And essentially what we've done is realize that there are 4 ways in which scholarly communities and practitioners view sustainability challenges. And 2 of them are based on some kind of economic logic. It's an economic problem of some way, the commons optimization schools. And they say that therefore, whether you can address the climate crisis, whether the evidence is actually there, requires then finding some kind of optimal outcome that improves cost-benefit analysis for society as a whole. And the optimization school has led to Nobel Prize-winning economist Nordhaus saying that the optimal answer for the climate crisis is 3.2 degrees Celsius. That's the best optimal outcome for the climate crisis based on an evidence-based approach to improve economic welfare. But of course, the scientists say that actually 1.5 is what we need, and that's what the governments have agreed to across the world. And that's not a compromise approach that the SDGs tend to engage in, compromising around different objectives. It's actually focusing the actual problem at hand. And it's realizing 1.5 actually is what has to be the justification for our evidence. And that we refer to as the prioritization school. And that school says begin with the problem itself, whatever the evidence happens to be, and then use your other data to reinforce that problem. So I want to ask you in your next 2 days, where are you going to place your work on monitoring and assessments? Where are you going to place it? Is it going to reinforce the type 2 approach or economic optimality, or is it going to find a way to actually close that gap between what's happening on the ground and our policy tools? So 1 minute left, I just want to then say the implications then for the work on inventories. So it turns out that there's a lot less attention to be given to the politics behind the IPCC reports on inventory guidelines. Unlike the assessment reports that are getting a lot of attention, the guidelines are actually almost buried in the background. And my student, Lee Hyona, actually found that that's a problem because the greenhouse gas inventory methodologies are all over the place, influenced by politics. Even the tier 1, tier 2, and tier 3 approaches and who uses them have political impacts. But tier 1 and tier 2 and tier 3 are very different. And many countries don't use tier 2 and 3, they use tier 1. And those are far too coarse to generate and use evidence-based knowledge. So one example, my colleague, Mark Bradford, found that leaf decomposition in forests vary within half a kilometer, such that you can't model across hundreds of kilometers. You have to actually get to that fine-grained level. In some cases, there's sinks, in some cases, there's sources. We just learned that Europe's turning towards now its forest towards being a carbon source, not a sink anymore. How did these get figured into tier 1, tier 2, and 3 methodologies? Not very well. In fact, the scientific evidence takes 2 years to show up in the guideline processes, even when you have tier 2 and tier 3 mechanisms. And for that reason, I've called for with Lars and Hyona a much more stronger approach to greenhouse gas inventories that links the different measures we do have in one common data set. That alone is key for addressing the climate crisis as a prioritization type 4 challenge, but it's not enough. You got to think then about how you link those to the policy tools that actually matters. And we're doing some work now there looking at the policy tools that emerge across countries and cities, along with what they're doing on their greenhouse gas inventory measurements. So with that, I'll stop because I'm running out of time. Are we sitting here or are we sitting here?
Yes, we are supposed to be sitting there,
Yeah.
all 4 of us. So yes. I'm sorry, I'm not being a very good moderator. The geography of this place confounds me. So, yeah, let's go. Then. All right. I don't speak good and bad. Oh, is it good? Okay, great. Thank you. Thank you very much, everyone, for those very interesting presentations. And we've really canvassed some very different topics. And it's hard work for the morning. So first, I would like to open the floor to the audience, both online as well as in person in this room. So for those people online, would you kindly type your questions into the Zoom chat? Is that the idea, Tom? So, yes. Sorry. And then the questions will appear somewhere, and I will be able to get those questions. Of course. And yeah, I just don't like people on the Zoom to feel like neglected. But yes, and in the room, would you kindly feel free to raise your hands or use your identifier. Just do this, and then I will somehow be able to see you. Yes, thank you. I would just like to start first. Great. Yes, over to you.
Well, thank you. Those were three wonderful talks to begin this GEMM Summit meeting. I have questions primarily for the first speaker, and I'm going to combine three questions into one, if you don't mind. I'm curious about, with the heat island effect, how much of that is just due to air conditioning, depositing heat into the atmosphere from the buildings, just pumping heat? How much of it is due to solar irradiance on the buildings, and can we modulate that by changing the albedo or reflectivity of the building? And then finally, I hope you don't mind, how much do urban greening strategies really allow us to modulate what's going on in the cities?
Well, okay, thank you very much. Can it be heard?
Yeah.
It's on? Great. Okay, three questions. How much is due to air conditioning? Not a lot. So this is the anthropogenic heat part of the entire energy balance. This QF or QH, or sometimes AH called, not QH, AH. Air conditioning is one part of building energy use, which is contributing to the anthropogenic heat, as cars give off heat, as we people give off heat, as the metabolic heat. So this is difficult to measure. So we have to rely on modeling studies to some extent on the anthropogenic heat and the air conditioning effect. But what has been shown, it's a minor part of the entire, let's say nighttime 4 degrees C, it would be less than 1 degree C of that, probably less than 0.5 degrees C even. So in terms of, can we change facades, for instance, can we change? So one of the cooling technologies or mitigation technologies that's being propagated is painting everything white, kind of, right? Reflective paint. It doesn't necessarily have to be white. There's other reflective paint which is not white, which would be much better and easier on the eyes. Again, we rely primarily on modeling studies for this. Again, it's a small part which could be mitigated by doing these kind of interventions into the system. It's not a major mitigation option. Greenery, urban green, vertical greenery, rooftop greens, greenery, parks, etc. It depends a little bit on the climatic context. So if you're in a dry city, Phoenix, Arizona, greenery will have a measurable impact due to providing shade, due to providing evaporative cooling. This is less prominent in the context of Singapore because we already have high humidity here, so evaporative cooling would not be very efficient. Providing shade due to greenery is good. I think the greenery effects, especially the ones on the building scale, like vertical greenery and rooftop greenery, is very micro scale, and it probably benefits sort of the interior microclimate more than the microclimate outside. When we talk about the urban heat island, you would have to install a lot of greenery to have a measurable effect on the urban heat island.
Hi, I'm from India. My question is just, I was curious to know, is there any relationship you have found in the climate change with the increase in the population or the trend of the population increase and the climate change?
Thank you for the question. So may I just clarify the question?
Yeah.
Are you asking about whether there's been any significant linkages between population growth and climate change?
Yes.
Okay.
And particularly the population density that in some areas, some pockets, the population density may be more, in some pockets, it may be less.
Thank you for the question. May I perhaps invite Eric first to take the question and then Faz and maybe Ben.
Well, yes, there is a relation between population density and greenhouse gas emissions, urban warming, and air pollution. Dense cities produce less pollution, less greenhouse gases. There is evidence that extended cities like those in United States increase enhance the emission, the use of fossil fuel for transport, building low capacity residences, increase the consumption of energy. Compact cities reduce these adverse effects. And now is an interesting point, how we define cities. And we have to look the pattern, the current pattern of cities. We have two trends. In developing countries, is happening that cities are becoming more dense. And the opposite is occurring in developed countries, like in Europe, where people are leaving the cities, are moving to the outskirts, looking for a less stress life, but they commute to the city every day. So that's an important point to consider.
Thank you, Eric. Perhaps I'll invite Ben first to come in from a policy perspective, if you have anything to add on that.
Well, I stand back a bit and think about this question in terms of both how the global system works, but then also how cities are part of broader historical context. So on the biodiversity side, one story is that as cities emerge, there's less pressure placed on rural areas as urbanization occurs. So we see this a lot in North America and in Europe, that in the rural areas, you get less pressure on those places. But then the point's well taken that at the suburban level, you get more impact. So if you just look at cities, you don't look at then cities as part of a broader migration pattern ecosystem, you can miss then what's important to think about and how to analyze then the broader impacts of cities, which go beyond cities themselves. But secondly, and important for Singapore, is that some countries are city-states. And this poses challenges and opportunities because imagine for a second that Singapore didn't leave Malaysia in 63 or 65. Okay, let's say it stayed part of Malaysia. Singapore wouldn't have the same attention it now has that it does get as a national country. It would be like, for example, Houston or Edmonton as a comparable unit. But as a city, as a country, it has a lot more attention at the global level. And that can lead to both benefits and negatives. Singapore has no natural endowments, the way a lot of countries do for hydropower and so on. So thinking then about how you would think about responsibilities matters in this kind of context. And actually, we're working on some ideas about how you might therefore do assessments of countries based on where they're starting from, their starting points, that might then help politically generate deceleration that recognizes those differences. But just some thoughts.
Thank you. That's really interesting. Would you like to come in and then I'll take more questions? Would you like to?
My question was that, for example, in India, we are increasing the urbanization. The urban population is increasing almost 35 to 40% of the total population. How, I mean, we feel that it is also contributing towards the climate change. That is one aspect. Second is the increase in the population. As of today in India, the population is almost 1400 million population. So that also is contributing towards the climate change, and that is to also the unplanned distribution of the population. So that is creating some sort of problems on the climate change. So that was my real thinking about that.
Well, your question can be answered at many different levels. So on the local level, yes, if you have more people in a smaller place, then densification of urban structures, yes, new cities being built, etc. That will increase the local temperature, no doubt about that, through the urban heat island effect, as I showed. On a larger level, the more people you have, the more fossil fuels will be burned to produce energy. That will increase CO2 levels, as we know, and hence, yes, this will affect climate change. And environmental problems are people problems. So the more people we have on this planet, the bigger our environmental problems are, and climate change is one of those problems. That's maybe my personal view, but I think there is a direct connection between the number of people and the environmental problems we have.
So my question is to Ben. You had mentioned about the equity crisis, the concerns, and later on you had also given a very good chart as to the historical responsibility, which very clearly depicted the 92% and the 8% ratio. So it is very evident in the latest COP27, where climate finance has become a very contending issue. So, I mean, what does it really portend, for the emerging scenario, especially in the context of, the developing countries and the small island nations, because that's really at the heart of this entire issue. So, your comments on that.
Oh my gosh. I'm working on a report on that great question right now. It should have been 20 pages. Now it's not like 80 pages. It's completely got insane because that's such an important question. So I guess some brief answers are, I'll be divide that into 3 different parts. So one is the responsibility issue for mitigation. And I think that there's 2 different competing claims. One is that equity shouldn't be part of that conversation. Whatever makes sense to lower carbon emissions is the most important way to go. But others say no, without equity in that kind of conversation, A, instrumentally, you won't get agreement. And B, it makes sense because why should you penalize the states that didn't actually do the cause the damage in this kind of responsibility question? But then, of course, the other one is the adaptation question. How do you then facilitate finance for adaptation? And then even more importantly at GEMM was the loss and damage question, that even if you don't do adaptation well, should you compensate in some way? And those 3 questions all affect the equity issue, but in different ways. And I wish we had more time to discuss them in detail, but I would say that we're losing these conversations when we, right now, for example, the carbon border adjustment mechanisms, to me, I'm very worried that they're actually going to be making things worse on the equity side and the just transitions side by blaming those countries that historically have not had as great impacts in the climate crisis because they haven't got the policies in place that the North does, who have more capacity. So to me, how would you design these mechanisms to actually reinforce just transitions and not undermine them is a really important question for both the mitigation and adaptation sides of the story. But my other worry is that by having this conversation on equity, we're moving towards the low-lying fruit of loss and damage. And we're kind of pushing away from the crisis of the cliff, which is going to affect everybody, equity, economic, and ecological challenges. So I would say there's so much to your question, and I look forward to talking more about it, but that's a brief response to, I think, a really important issue. Equity can go in both directions. It can make things worse in terms of how we talk about it, or it can make things better.
Do we have any questions online? Yeah, sorry. One. Yeah, it's under the chat. So if someone could click on the chat, so that would be perfect, David.
The question is, the first question is from Professor Liebling, University in China. This question is specifically for the first speaker, Dr. Roth. Additional heat flux from the urban area intensifies convective rainfall. What is the underlying mechanism?
How much time do I have? 2 minutes.
2 minutes.
That's not bad. Underlying mechanism. There are a number of things that are different in the urban area. First of all, yes, we have more convection to heat down. We have more convection, so we have more uprising air. which is already one of the main ingredients to have a rainfall. Secondly, in the city, we have an above average amount of condensation, cloud condensation nuclei because of air pollution. That also contributes to the possibility of more rainfall over cities. In the case of Singapore, because of more convection, we have more convergence or inflow of air from the surrounding areas, and that air is coming from oceanic surfaces which carry a lot of moisture with them. So we have an influx of moisture which then can condensate in these updrafts into rain. So it's these kind of processes which create the enhanced rainfall. Convective rainfall in this particular case.
Thank you. And do we have, oh yes.
Hi, Ben. My question is for Ben. I'm Linda from APSAL. Would you kindly elaborate the IPCC 1.5 and the 3.8
3.2?
3.2 temperature? I didn't quite understand it as an IPCC author.
Yeah.
I know that we, like in IPCC, we do not do the research ourselves, but we sort of like gather, assess whatever research that is already out there and find the most reliable one,
Yeah.
and then we use them in our reports.
Yeah.
So I would like to get more elaboration on that.
Yeah,
Thank you.
and again, I wish we had a couple of hours, but the main point I was making is that different scholars and practitioners bring different adjudicating frames into their evidence, how they look at the evidence. So Nordhaus, who's an economist, his key starting point is, how do I think about the climate crisis as an economic welfare undermining event? So he is curious about then what are the optimal policy solutions based on the economic damage that's been caused by the climate crisis. And he and Nicholas Stern, as you know, go back and forth on the discount rate based on how to then extrapolate whether it's economically rational to address the climate crisis, mitigate that is, or whether it's cheaper to adapt or not. And they all do it on the basis of economic welfare as an ultimate dependent variable. How do I enhance economic welfare overall? And Nordhaus then argues that the most optimal policy response, given his modeling, will get us to 3.2 degrees Celsius as the optimal outcome based on this mitigation adaptation scenario. So it's evidence-based, it's data-driven, and he says the rational answer for a policy response will be a 3.2 degree warmed world, nothing higher. But the ecologists who don't do economic welfare, they just do catastrophic tipping points, say that no, 1.5 is the actual objective based on the science of the catastrophic tipping points that the IPCC has talked about, right? Also evidence-based, data-driven. Now, Paris happened to go along with the ecologists, basically, and said the modeling is such that that's going to be what we need. And of course, they then said it's going to impact the economy as well. They absolutely, right? But they began with the catastrophic ecological processes that would undermine all of us, right? Two different approaches to data and evidence led to two different ideas about what was the optimal response. And my point is, without thinking carefully about how your own cognitive frames influence your data collection, you may accidentally go towards a Nordhaus orientation and not an IPCC, a Paris Accord orientation. And they're both legitimate, eh? They're both actually based on strong moral foundations, but how they see the data and how they apply data and what data they collect is very different. And that's kind of what I meant. Does that help? Yeah, okay.
Thank you very much, Ben. I think I have the honor of calling this panel discussion to an end. Before I do so, I'd like to invite everyone to join me in thanking the speakers for what I think we can all agree is a very good start to the summit. Thank you very much for your time. We'll just accentuate the fact I'm very sure.
Right. So thank you very much for the Singapore session. So we're going to take a break, coffee break, and we come back to the session at 11. Right. The coffee outside. Again, for those who participate in virtually, we'll come back to the discussion in 11 o'clock. Thank you very much.